Hi everybody, and this is lesson 8C on probability. And in probability we usually have some kind of experiment where you can observe a result, and each repetition each time you do that experiment is called a trial. The results are called outcomes, and the set of all possible outcomes is called a sample space. So you might, like throw a die or spin a spinner or toss a coin or pick a deck or pick a card out of a deck or pick several cards out of a deck. That would clearly make the sample space a little bit more intriguing, that's for sure. For something as simple as tossing a coin, there's really two outcomes, either heads or tails. And that's your sample space right there. If you've got the spinner at the right, so if you spin the spinner and you observe where the arrow is pointing when it stops, you've got two possible outcomes here. And those possible outcomes, or three possible outcomes rather, a 1, a 2, and a 3. And I'll have to get this mimeopad going here. Maybe it likes me today, maybe it doesn't, I'm not sure. Okay, get those braces going. And you could have the gender of a 3-child family be the outcome of an experiment, so to speak. I know that sounds kind of awful when you're talking about children, but it could be 3 girls, and you could have 2 girls and one of the children be a boy, or you could have 2 boys and one of them be a girl, or you could have all 3 boys. That's entirely possible that those are your outcomes when you have 3 children in a family. Now, another interesting possibility would here be if order matters. Okay, so if order matters here, then suddenly the order in which the children are born take on a little bit of significance, and there might be some different outcomes possible there. I mean, you could still get all 3 children being girls. That's possible. Or you could get the oldest being a boy with 2 younger sisters. Or you could get the boy being born in the middle of 2 girls, thorn between 2 roses. Or you could get the littlest brother and 2 older sisters. And you can put the shoe on the other foot here as well, so to speak, with 2 boys and a girl. It could be the girl is the oldest of the 3. It could be that the girl is the middle child of the 3. It could be that the girl is the youngest of 3. And, once again, the case where all 3 of them are boys. So that sample space takes on a different look if order matters, and that would be what we have here in red, would be that particular sample space. So that's kind of interesting to think about here. And the event that you get at least one boy born that's exactly what it's called, an event, where it's a subset of the sample space. So the event that you get all 3 girls, that is one particular possibility. In the case of tossing a coin, one event could be heads, the other one could be tails. So if you've got a die that's numbered 1 through 6 and you roll that, the possible events where the die shows an even number is when you roll a 2, you roll a 4, or you roll a 6. Those are the possible outcomes of that set. If you show a number less than 5, well, that could be 1, 2, 3, or 4. And that would be that event right there. If you're talking about a multiple of 3, well, you're talking about either rolling a 3 or rolling a 6, because those are the only 2 multiples of 3 that are on a die numbered 1 through 6. All right, so let's kind of think about another way to write a sample space, and that would be this example down at the bottom here. So suppose that you have a coin that's flipped until both a head and a tail appear, or until the coin has been flipped 4 times. Okay, so if the coin is flipped exactly 3 times, then that means you get the same thing on the first 2 and something different on the last, because you're flipping the coin until you get both a head and a tail. So if you flip it exactly 3 times, then that means you got 2 tails and a head, or vice versa. So those are the only 2 outcomes there that satisfy this event. Okay, now if you flip it at least 3 times, then that means you flipped it 3 or 4 times. Okay, so we've got all these outcomes, which are the same ones from here, where you get 2 heads and a tail, 2 tails and a head. Now, if you flip it 4 times, let's go back to the rules here, you could end up with 3 heads and a tail, or 3 tails and a head, or you could get all 4 heads. You could get no tails whatsoever in 4 tosses, or the opposite can happen. You can get 4 tails and no heads to your name in that situation. So 6 possible outcomes satisfy that event. Okay, now lastly, this event, the coin is flipped fewer than 2 times. Well, if you think about it, that means fewer than 2 times means once. But that's not going to be possible here according to the rules of this little game, because you've got to keep going until you get a head and a tail both. So if that's the case, flip fewer than 2 times, well, that is not going to be possible. So that event set is called the empty set. No outcomes satisfy that. So that will never happen in this particular case, because you have to flip it until you get both a head and a tail. All right, so that's not really too bad to do. To just kind of start thinking about events and sub-events, or excuse me, events and sample spaces. And if you wanted to describe different events in words, you certainly could. So, we've got this situation where we've got a study of workers earning minimum wage, and they're grouped into various categories. E would be the event that the worker is under 20, F would be that the worker is white, and G is female. So if we're talking about these particular events, again, remember this is the complement of E, so that means that we're talking about everybody that is, well, I probably should rephrase this a little bit, because if they're under 20, then that means everybody that's in the complement would be 20 and over. If we're talking about F intersect G, that would be where you have both qualities at work here. So in this case, we would be looking for the workers that are both white and female. Okay, now remember this other symbol in C, that's a union, which means we're going to put it all together, so it's going to be a bigger set. So they are either white or they are female. So we're going to have a much larger set here, because we're going to take all the workers that are white that are making minimum wage, or we're going to take workers that are female. So we might have some men in this set, and we might have some ladies that are not white in this set as well. I like that set a lot better because it includes more people, but that's just me that's talking. More people you get in, the better. That's just my opinion. So now we have mutually exclusive events, and mutually exclusive events would be events where the intersection is an empty set. So the best way to think about this is no outcomes in common. No outcomes in common. So, are the events in the prior example mutually exclusive? Could you get workers that are under 20 and white? Well, sure. Could you get workers that are under 20 and female? Absolutely. Could you get any combination of those? Yes. So we could say that no, these are not mutually exclusive, because If they were, they'd have no outcomes in common. Now, if you look at this other one, rolling a die and flipping a coin, yes, they are mutually exclusive because rolling a die usually gets you a number 1 through 6 and flipping a coin gets you heads or tails. So nothing is shared by those two at all. Nothing is shared at all by those two. All right, so if we're going to talk about the idea of probability, it's a very simple thing to do. You have to count the number of events or outcomes in your event set, and you have to divide it by the number that's in the sample space. So this is probably pretty easy to do. If you roll a 6-sided die, there's your sample space. So the number that is in your set S will be 6. And the number that would be even out of all of those, if event E is an even number, that would be 3. So you're going to take the number in E, which is 3, and divide it by the number in your sample space, which is 6. And since today's a day that ends in Y, we're going to reduce that down to 1/2. And again, this isn't really too hard to do. If you've got a number that's less than 7, well, for crying out loud, all of them are less than 7. All 6 of those are less than 7. Okay, so that's going to give you a probability of 6 out of 6, or just 1. And what that does is this makes this a certain event. That means every time you conduct this experiment, you are certain to get a number that is less than 7. Okay, now we're not accounting for 0 and negative numbers here, so we're going to kind of toss that part out. But it definitely satisfies the event that you're going to get a number less than 7. Okay, now how many outcomes have an 8? Well, no outcomes have an 8. So the number that are in set G is going to be 0. No outcomes have an 8. So 0 divided by 6 is 0. And what we say here is that this makes this an impossible event. Okay, an impossible event to take place. So probability of 1 certain, probability of 0 impossible, probability somewhere in the middle. Probably the most likely scenario that we're going to have, honestly. Okay, that takes care of that. And again, very simple, straightforward probability questions that you can expect to see in this section. Just got to think about your sample space. And honestly, one of the hardest things to think about in a sample space, and sorry, I pushed the button and went all the way back there, no big deal. Probably one of the harder things to think about is a deck of cards. And I know not everybody plays cards. I'm a big card fan myself, so you know, this is like old hat for me. But for somebody that doesn't play many card games, a standard deck has 52 cards in it. There are 13 of each suit. And one suit is called spades. It's the black suit that looks like an upside-down shovel. You have diamonds, which are a red suit, clubs, which are another black suit, and I've had friends call those puppy toes, which they kind of look like it, and then hearts, which obviously are another red suit. The deck has ace all the way up through king, so ace, 2, 3, 4, 5, etc., etc. And these top 3 cards, jacks, queens, and kings, are called face cards. And the reason why is because they have pictures of faces on them typically when they're printed. Now, some games aces could be low, some games aces could be high. It just depends on the card game you're playing. But the bottom line is there's a nice little bit of symmetry about this, and once you get used to it, it's not too much trouble. So there are 4 aces in the deck. So if you want to draw one card out of this deck at random, let's say you shuffled them up, there's 4 possible aces that you could draw out of the 52 cards, and this fraction reduces all the way down to 1/13. Now, if you're never sure if you can reduce a fraction, may I recommend that you go to your calculator and hit Math, Enter, Enter. Okay, under the Math menu of your calculator, you should be able to reduce a fraction to lowest terms, if that's something that eludes you to do by hand. Okay, the probability of getting a face card. Well, a face card could be any one of these Jack, Queen, or King in the 4 suits. That number's 12 of them. Okay, and so let's see here. 12 out of 52, and then I can reduce that down all the way to 3 over 13 because the common factor there is actually 4. And that's how you get the probability of getting a face card. Okay, so if you cut the sample space down to just a single suit, 3 out of the 13 would be face cards. All right, now lastly, this is kind of phrased poorly. I'm just going to do or. If you want to do a spade or a heart or a 3. Well, now this is where things get a little bit interesting because getting a spade is 13 of the cards. Getting a heart is 13 of the cards. Now, these two are mutually exclusive from each other. A card cannot be both a spade and a heart at the same time. They must be of either the same suit or different suits. So getting a spade or a heart, that means you're going to pick one of those 13 plus 13 or 26 cards, the 13 spades, the 13 hearts. Now, if you're going to pick a 3, you might notice that you've already included some 3s in here, and this goes back to that double counting that we talked about on the previous video. There are 4 3s. But if you stop and think about it for a moment, you've double counted 2 of the 3s. You've double counted the 3 of spades, you've double counted the 3 of hearts, because you put the 3 of spades in here and the 3 of hearts in here, and you've also put those in there. So because I have double counted, I need to take those away. So I'm going to end up with 28 out of 52, if I can get it to write correctly, 28 out of 52. And that's going to be the equivalent to 7 out of 13. And that's the probability of getting a spade, a heart, or a 3. So I recommend that you get to know this picture pretty well. And I've got a few decks of cards in the classroom that if you just wanted to kind of get your hands on it and move your way through it, that would be fine as well. And I'd be happy to have you do that. We're going to do an experiment, or we've done an experiment already where we have sorted cards, which has probably helped you a little bit there. Okay, now the last thing in this lesson is a very simple thing. It's called empirical probabilities. And in many real-life problems, it's not possible to establish exact probabilities. In fact, what you might do is drawing upon your past experience, and that's called empirical probabilities. So you take a look at the number of different injuries that have occurred here, and this is quite a large number of injuries that have occurred. And if we want to find the probability that a randomly selected person was hurt on a with recreational equipment here, was hurt on a trampoline, well, we know that trampolines accounted for 107,345 of these injuries based on what we know here. So what I have to do is to figure out the probability that I randomly pick someone that has injured themselves on a trampoline. I've got to add all of those together, all of those rather large numbers together, and I'm working on doing that right now as we speak. And there were a total of 903,887 injuries. Okay, that's quite a lot of injuries if you stop and think about it. So only 107,000 of those were, I say only 107,000 were trampoline injuries. So what I need to do to find the probability that I get this situation is 107,345 divided by 903,889. So 107,345 divided by 903,889. And that gives me about 0.118 probability. Okay, so that's the lesson, and when you get a chance, start working on the practice problems. Good luck.